All right, we should get started. I don't know, for the remote side, I don't know how many of you can hear me, but I just sent an email to all attendees. You know, the slides for the first lesson is now online, so you can go to the website and download them. Excuse me?
Somebody get ready to copy. Could you give us the website very slowly and we'll copy it down?
Yes, I can. It's http and colon /knowledge_transfer/short course, one word, dash my last name, ZHANG. Okay, and from there you can you go to the attachment section. You can find lesson 1 physical formulation.ppt. Did that help?
Sorry, once more. We didn't get your last name.
Oh, okay, we got it.
Okay.
Yeah.
Yeah, it's a short course dash ZHANG. Okay.
We go to online.
Thank you.
Sure.
Can you download?
Yes, you can download, yes. Go to the attachment and you can find lesson 1 dash physical formulation.ppt. Okay?
We already got it. Don't worry.
Okay, good. Before I start, can I know who are out there? Harry?
Okay, Joseph, this is Harry Wang. We are from Virginia.
Okay, good.
We have 6 students here. We are looking forward to this very good training course.
Thank you, Harry. How? Anybody from Portugal? Not yet. How about OSU? No. Yes. You probably still having. Oh. Okay, we can hear you, Yvette.
Can you hear me?
Yes, we can.
Okay, good.
Okay. So let's get started. We are now on slide 1. Okay, I announced the slide number because this course is being audio taped. So for other users to learn offline. So I will announce the slide number as we go. So if you cannot see us, you know, at least you can follow us by the slide number. So this short course will be comprised of 4 parts. The first part is on the physical formulation, and second part is on the numerics, and third part is on the code, and the fourth part is on the tutorial. Okay, and I believe all of you have received the outline of the course. So before I begin, I like to mention that if you have any questions, this is really a good time to ask. Okay, so because we are going to very deep into the inner workings of the model. So it'll be good, a really good time for you to ask very detailed questions. Okay, now we are on slide number 2. That shows all the governing equations for that self-model solves. Okay, the continuity equation, the momentum equation, and the equation of state transfer, the transport equation, and the turbulence closure equations. So we'll go through those in the next couple of slides in detail. Okay, so just briefly, just explain the symbol. The coordinates we used is pretty conventional. You know, the origin is placed at the undisturbed mean sea level, and x pointing to the east, y to the north, and z vertically upwards. And the bold u here stand for the 2 components of the horizontal velocity, or horizontal velocity vector. And w is the vertical velocity. and eta is the free surface elevation, and h is the small h is the water depth. Okay. So okay, let's go to the next slide, slide number 3, which kind of shows funny. Let me just. All right. The continuity equation is nothing but the conservation of volume. Okay, it's derived from the conservation of mass originally. So if you take an infinitesimally small box with a size delta x, delta y, and delta z, as shown on the picture here, then you can basically keep track of the mass coming in and coming out. Okay, so if they must balance each other out. That's what this equation on top says. Okay, so the total mass change during a particular time step delta t must be explained by the mass coming in, mass flux coming in from the 6 surfaces of the box. And if you further simplify it, you get immediately get this Euler-Lorentz form of the equation here, the differential equation here, by taking the delta t and delta v, the volume of the box, going to 0. So just very briefly, for those of you who are not familiar with the two frameworks of fluid mechanics, the Euler-Lorentz form means that you are standing fixed in space and taking snapshots of the flow field. Okay, whereas Lagrangian form means that you are traveling with a fluid particle or parcel and observe the change of the flow field. So those are the two fundamental frameworks in fluid mechanics. So inside the Lagrangian framework, then you can the continuity equation expressed by this total derivative, d rho and dt. That's total derivative. That means you are taking the, sorry? That means the you are actually observing the change of density by traveling with one of the fluid particles. Okay. So the total derivative of the density is can be expressed as the sum of the partial derivative d rho dt, that's an Euler-Lorentz form, plus the advection term. So Laplace 3, that a gradient operator means it's a 3D gradient operator. Okay. If without 3, that means a 2D. So that's the convention I use. So now if you further assuming that the density does not change very much, that's so-called Boussinesq assumption, then the continuity equation is simplified as this. Okay, this is the continuity equation for the incompressible flow. That says the flow field must be divergence free. Okay, so you by the Boussinesq assumption, you reduce the mass conservation to volume conservation here. And because the free surface elevation is part of the unknown, we are dealing with free surface flow, so we need to have an equation for that. To do that, we just vertically integrate the continuity equation. Okay. Now here, the gradient operator. We are looking at the bottom equation. The gradient operator is only applied to the horizontal components. Okay. And W, of course, is the vertical velocity. And then you utilize the vertical boundary conditions, the two kinematic boundary conditions, and the surface and bottom. Okay. So very briefly, for example, at the surface, Z is a function of x, y, and t, right? And then, so the W, the vertical velocity, is the total derivative of Z with respect to t. Okay, this is, again, this is a Lagrangian framework. And because of the chain rule, you can get this 3 terms coming out. And the bottom, you treat the bottom similarly. Those are the two bottom kinematic boundary conditions. And then you plug these boundary conditions into this integrated continuity equation, and finally arrive at this form by using the Leibniz rule. Okay.
Using what rule?
The Leibniz rule. So you basically put this gradient operator outside, but because you put outside, the extra term will come out, right? This is this equation, the bottom equation. That's Leibniz rule. Okay, so the equation inside the red box is the typical is what we use typically for the integrated continuity equation for the surface elevation. It has a very simple explanation. Okay, you basically take a vertical column from bottom to free surface, and what this equation says is that the change of free surface elevation must be explained by the net flux coming in, right? Okay, now we go to slide number 5, the momentum equation. The derivation of a momentum equation in fluid mechanics is rather complex, especially the parts relating to the constitutive equation for the internal stress. But very briefly, momentum equation is nothing but glorified Newton's second law. Okay, therefore equals ma. A is the acceleration. So if you take a fluid parcel, infinitesimally small, okay, and the rho dV here is nothing but the m, right, the mass, and u is the velocity. So d dt here again is total derivative in Lagrangian sense. Du dt is nothing but the acceleration, right, and must be balanced by the body force here, the second term, as well as the internal force. For example, the pressure and the stress. Okay, so after you apply the constitutive equations, you get this equation. Again, this is the total derivative, and this is the pressure gradient. So the internal force term is split into the pressure term and stress term here. Okay, through the constitutive equation, and last term is a virtual force due to the Earth's rotation, because Newton's second law only applies to inertial framework, right? So Earth is not. Earth is rotating. So last one is the virtual force. The small f is the Coriolis factor. And for the vertical component of the momentum equation, it looks similar, except that you don't really have a Coriolis. I'll explain that later. And then these differential equations are fairly complex and very involved. They are all fully coupled. They are nonlinear. So one of the typical assumptions we make is so-called hydrostatic assumption. Okay, basically we take the vertical momentum equation and we neglect the advection term, we neglect the mixing term, the viscosity term. So that will result in the balance between the pressure gradient and gravity. So if you integrate this equation, you get the hydrostatic pressure is nothing but is a function of the density. Okay, so in the mechanics, if you remember, it's the pressure equals rho gv. This is very similar. Okay, rho g and h. Sorry, it's rho g h. H is basically here, right? The height difference. Of course, during integration, you also have a constant coming out. This constant is nothing but the atmospheric pressure and free surface. Now, in geophysical fluid dynamics, we typically concerned with a fluid of very different scales, okay, in the horizontal and the vertical. So we like to codify that through the separation of scales. So if you take the momentum equation, it looks funny here. Apologize for that. This morning I just rearranged the slides and insert a slide number, and it changes everything. Okay, so the only thing we did here during the separation of scale is that we basically recognize that the vertical mixing term, vertical viscosity term is different from the horizontal viscosity term here. Okay, so we use different viscosity symbols. The horizontal is mu and the vertical is nu. Okay, and horizontal viscosity is usually much larger than the vertical velocity. So so if you take the you apply the hydrostatic assumption and put into the momentum equation, the horizontal momentum equation, you get all those terms coming out. The third term, Coriolis, this is Earth's tidal potential. It's another body force. I'm not getting into detail for that. And this is a atmospheric pressure gradient here. Okay, and then the fifth term is a due to the density difference. So that's baroclinic term. And last term is the horizontal viscosity term. Okay, and if you remember, we use this Boussinesq assumption. Basically assumes that the density of the fluid is more or less constant, but except for this baroclinic term. Okay, because that's this natural density difference is one of the major driving force in many flow regimes. So as I explained, now we are on slide number 6. Coriolis is a virtual force. Okay, it's because it's not a real force in the sense that it's only a result of Newton's second law not applying to the inertial frame. In other words, it's due to the Earth's rotation. And in GFD, geophysical fluid dynamics, Coriolis is an extremely important term because it's responsible for a number of very unique phenomena. So very briefly, how you get this Coriolis, if you review the lessons in classical mechanics, in a rotating frame, okay, the total velocity is expressed as two terms. The relative velocity, that's velocity observed in a rotating frame. Okay, plus the velocity due to the rotation, and omega is the angular frequency, and r is the field vector. Okay, and then you take a derivative of u, you get the acceleration. Then you get these two terms coming out. Okay, so a, small a.
Ok. Já temos coisas.
Is that Annabella?
Hi, Joseph, Ligia is talking.
Ligia, hi. Hi.
Hi.
Are you guys able to see the slides at all?
Yeah, not very good, not very well, but...
Well. Wow. It's we can hear lots of noise from your side.
They just see the camera pointing up here, so they'll need to have the
Okay.
address to be able to-
Yeah, I'm going to tell them. Okay, so Ligia,
Yeah? Joseph?
I just sent a note to every attendee. The slides are actually online. You can go to the website and download them. Okay.
Okay.
Yeah. Do they need to mute their system? Maybe. Ligia, we can hear lots of noise from your side.
Yeah,
So
don't forget to mute.
yeah, don't forget to mute your speakerphone.
Okay. Okay.
Okay, so let's continue. So if you take the time derivative of the velocity, you get the acceleration. So acceleration is comprised of 3 components. The small a here is the observation observed in the rotating frame. Okay. Other 2 terms are due to the centrifugal acceleration. So typically in GFD, if the scale is not global, we typically use this F-plane approximation. That means we neglect the curvature of the Earth. And we then project the Earth rotation vector into the local frame. So you get the two components, one along the y direction, another one along z direction. So if we apply the theory we outlined on the previous slide, then there are three components of Coriolis acceleration. Okay, x component is f star times w minus fv, and y component is fu, and z component is minus f star u. Okay, f star and f are Coriolis factors. And typically, because the vertical velocity is much smaller than the horizontal velocity, we neglect these f star terms. So for the two horizontal momentum equation, the acceleration due to the Coriolis minus fv and fu. Okay, so that's the cross product of the Coriolis Coriolis factor and the horizontal velocity. So as Coriolis, of course, is very important in the GFD and explain lots of unique phenomena. And one of them is inertial oscillation. Okay, so if you have like a sudden shutdown of the coastal wind, okay, there's no external force, then because of the inertia, okay, the flow motion will persist. If you neglect the viscosity term, you get this simple equation system. You solve them, you get this u and v component as a wave-like sine and cosine functions. Okay, so if you this picture shows the flow pattern you observe in inertial oscillation. It's circular, and strangely enough, you would think that the flow is rotational. It's not. Okay, the rotation of the flow field is actually zero, so it's irrotational. Okay, don't get confused with that. Okay, so the differential equations, of course, need boundary conditions. So we differentiate the vertical boundary condition from horizontal boundary condition. Vertical boundary conditions are pretty important in the numerical models such as self. Okay, so we will pay more attention to vertical boundary condition. And the surface, so you got a balance between the internal Reynolds stress and the wind stress at the surface. At bottom, you got the balance between the Reynolds stress and some kind of parameterized form. Okay, on the right hand side, CD is drag coefficient. So UB is the bottom velocity. Okay, so this is a classical quadratic drag law on the bottom. We'll talk about that next. So here is just basically what I took from the paper. Okay, so we just want to show you that the main point here is that the Reynolds stress is constant inside the bottom boundary layer. Okay, you start with the logarithmic profile of the velocity inside the bottom boundary layer that has a thickness of delta B. Okay, so Z0 minus H and the delta B minus H represent the bottom boundary layer. And U is a logarithmic function of Z. And then you take derivative, you can calculate the Reynolds stress in this form, and then you apply the boundary conditions in a turbulence closure theory. Then you get this equation inside the red box. So it looks complex, but essentially it says it's a constant inside the bottom boundary layer. And from this equation and the parameterized form of the bottom boundary condition, you can calculate the drag coefficient CD. This is a classical formula for CD here. Okay, let's go on to the next slide. This picture shows the CD, the drag coefficient, as a function of the bottom boundary layer thickness as well as the bottom roughness, Z0. Okay. Of course, as you can imagine, the larger the bottom roughness, the larger the drag is. right? Yeah. The larger the drag is, and the larger the bottom boundary layer thickness is, the smaller the drag will be. Okay. And typically for coastal ocean, people like to use a value of 0.0025, a constant for CD. But you can see that actually CD varies a lot with respect to the two parameters. And when the bottom boundary layer becomes very small, this drag coefficient can be very large. Okay, so that brings us to a major difference between the 3D model and the 2D depth average model. Okay, a 2D depth average model, you don't have this kind of at least you don't explicitly use this kind of drag law, and then because the bottom boundary layer is not resolved, so that when you vary the drag coefficient, you don't really have a bottom boundary layers. But for 3D, you do have a bottom boundary layer. So when you vary the bottom boundary layer thickness, the CD, strictly speaking, should change, right? That's something absent in the 2D depth average model. So in self, you have the option of specifying directly the CD, the drag coefficient, or specify the Z0, the bottom roughness. If you specify Z0, then when you change the vertical grade, because the bottom boundary layer thickness is assumed to be the thickness of the bottom cell. Okay, we assume that your vertical grade is able to resolve the bottom boundary layer. So when you change the bottom vertical grade, the CD will be automatically updated if you specify Z0, right? Whereas if you directly specify CD, CD will definitely not be changed when you change the vertical grade. So you may observe some differences in the elevation, because elevation is the elevation is dependent upon the bottom drag. So next slide, number 10. The transport equation is a classical advection diffusion equation. Okay. So the advection term is inside this total derivative, whereas on the right hand side I only show the this is the first term is a vertical viscosity term, and the last term is a horizontal diffusivity term, and Q dot is a source term. Okay. And very briefly, how you derive this diffusion? It's due to the Fick's law for diffusive fluxes that goes back to the random walk theory for the Brownian motion, basically molecular motion. But in our case, in GFD, we assume that the most of the diffusive flux actually is due to turbulence flux. Okay, turbulence flux dominates the molecular flux in a random walk. So visually, that's what you expect. If you take an initial profile of a concentration of some kind of tracer here, and if you neglect the diffusion, then it's just when you have a pure rotational flow, then the pure advection will result in pure translation. Okay, no change of profile of the tracer concentration. Whereas if you add diffusion, the amplitude will go down. If you originally have a Gauss-Hill profile, the amplitude will go down and the standard deviation will become larger. Okay, so that's what you expect with diffusion. And the vertical boundary conditions for the transport equations are relatively simple. On the bottom, we typically impose a no flux boundary condition. And on the free surface, well, it depends on what kind of tracer you are dealing with. For salinity, you may have evaporation and precipitation, and for temperature, you may have various atmospheric flux, okay, which we'll talk in the next couple of slides. Now, slide 11. So if the tracer is a salinity, we're dealing with salt transport. then the surface boundary condition becomes like this. Okay, the E and P are the evaporation rate and precipitation rate. Okay, the difference will explain the net flux. Rho zero is a reference density of the fluid. And if you are dealing with a heat exchange model, the temperature, then the surface boundary condition is a little bit more complex. This H dot is comprised of 4 components, which we'll go into detail for the next couple of slides. Basically, it's infrared flux and sensible heat due to latent evaporation, and the turbulence flux. And in addition, for temperature equation, for heat transfer equation, we also treat the short wave radiation term as a penetrative force. So it's a body source term. Okay, Q dot, you have a Q dot term here. And SW is the let downward solar radiation at the surface. So this cartoon basically shows the various atmospheric fluxes for temperature. And the air-water exchange, of course, is a big topic. I'm not going to go into too much detail, but briefly, the variations in the atmospheric pressure over the domain, a gradient of the atmospheric pressure will affect the free surface height due to the inverse barometric effects. Okay, so the momentum also is affected by the air-water exchange due to the surface drag, of course. And for the temperature, the heat flux comprises of various components. Okay, as I explained, you have a short wave radiation force, which is penetrative, and other 3 fluxes that only apply to the surface. And also, air-water exchange also affects the water mass due to the evaporation and condensation and precipitation. Okay. So that would, strictly speaking, you should modify your momentum equation to account for that. It's all good. Okay, so next slide is on the solar radiation. And solar radiation is typically forecasted. Okay, it's not measured. And depends on the time of the year, time of day, and the weather condition, latitude, and etc. And we basically make a simple assumption that the upward solar radiation part is a simple function of the downward. So by introducing the concept of albedo, alpha there. Albedo is basically a measurement of reflectivity of the water surface. And it's dependent upon the solar zenith angle at the state. And so the let downward solar radiation flux is expressed in this equation, 1 minus alpha, because alpha times SW is the upward part. So let downward part is 1 minus alpha times these exponential functions. And the parameters in this profile, for the vertical profile of the solar radiation, are summarized in a number of papers by Gerloff and Paulson and Clayson and others. And this table shows the different choices of those parameters, R and D1 and D2. D1 and D2 are 2 attenuation depths. Okay, so when you go from the top of the table to the bottom of the table, the water basically getting progressively dirtier. Okay, so it becomes more turbid. So as a result, the attenuation depth D1 and D2 is reduced. Okay, so graphically, this is 3 curves shows the vertical profile of the solar radiation for Gerloff type 1, 2, and 3. Okay, type 1 is clearest, whereas type 3 is dirtiest of the 3. Okay. Jeez. Okay, next slide. The infrared radiation has two components, the upwelling part and the downwelling part. The downwelling part usually is forecast by a weather forecast model, and it's a function of temperature, air temperature, and cloud cover and humidity. And upwelling part we typically treat this part using the simple black body radiative flux theory. So it's a function of the air surface temperature, TSFC. Okay, it's proportional to TSFC to the power 4th. And epsilon is the emissivity, and sigma is Stefan Boltzmann constant. So that's just a simple assumption here. Okay. So next slide, we are left with two surface fluxes, sensible and latent heat. Okay. And those two fluxes are parameterized by the bulk aerodynamic formulations. For example, in SELF, we typically use Zen's aerodynamic formulation. Okay, so in general, the turbulence flux are a function of surface air temperature and surface water temperature, and near surface wind speed and surface atmospheric pressure and humidity. Okay, so they are basically parameterized. Okay, in this using the similarity theory. Rho A is the air density. CPA is the specific heat of the air, and U star, T star, and Q star are scaling constants. Okay, U star is a frictional velocity, and the T star is the temperature scaling, and the Q star is the humidity scaling parameter. LE is the latent heat of evaporation. So if you use this bulk aerodynamic model, you need to iteratively solve for those scaling parameters before you can get the sensible heat and S and E to term.
Can you say
Yes.
what, briefly as possible, what similarity theory is?
Similarity series is basically assume that the fluid of different scales are similar to each other if the dimensionless parameters are the same. You know, fluid usually governed by the dimensionless parameters, right? Yeah, you assume that the fluid different scales are essentially the same. You know, if the dimensionless parameters are the same, that's symmetry.
The flows of different scales are the same?
Different scale, like a very large, you try to reproduce, for example, you want to try to reproduce the large scale geophysical fluid phenomena in a lab setting. So you need to scale everything down, right? You cannot build a lab of several hundred kilometers long. So then you apply the similarity theories. Just make sure those dimensionless parameters are the same, like a Reynolds number, a fluid number, all those kind of things.
So you don't scale them with Reynolds, the dimensionless parameters with the
You
changing scale?
no, you don't want to scale that. You want to make those parameters the same.
Okay.
Yeah, but those parameters are a function of the physical scales, right? Like the length scale and the velocity scale, all those kind of things. Yeah, so you can scale those things, but make sure those dimensionless quantities are the same. Okay, so after you iteratively solve those scaling constants, then you can get this S and E. And in addition, you can also get this, once you know the frictional velocity, you also can calculate the wind stress on the surface. That's one of the product of aerodynamic module. Okay, and of course, you can also use a much simpler formulation for the wind drag formulation. For example, the Pond and Picard gave this quadratic drag law. Okay, and CDS is analogous to the bottom drag. So in this case, it's a surface drag, and which is a function of wind speed. UW is the wind speed. Okay, and the UW prime is clipped. It's basically applying some kind of a bond by admitting that this theory is limited for a certain wind regime. Okay, next slide, number 17. Okay, so those two tables basically summarize all the inputs for the heat and momentum exchange model. Okay, you basically need the forecasted wind speed and 10 meter above mean sea level, and atmospheric pressure reduced at mean sea level, and air temperature and humidity and 2 meters above mean sea level. So those the table shows various forecast model we get for our to apply to the self model. So most of them are forecast model, and the last one, LAR model, is actually a hindcast model, real analysis. Okay, as you can see, that they come with different temporal and spatial resolutions, and they cover different regions, and they cover different periods. Okay, but those are all available internally here at OHSU. Next slide. Okay, turbulence closures is a very active research area. So I'm not going to talk too much about the turbulence closure theory per se. But very briefly, I'd like to introduce you to some important dimensionless quantities, such as this Richardson number. Okay. So one of the simplest turbulence closure theories due to the Pawlowski and Philander basically is based on the assumption that the turbulence is governed by the balance between the stratification and shear. Okay, so this is classical Kelvin-Helmholtz instability that occurs at the interface of two fluids. Okay. So the relative importance of shear and stratification is measured by this Richardson number, Ri. On the top you have the buoyancy frequency. On the bottom you can see that's the shear frequency. Okay, so if Richardson number is less than a quarter, then the fluid becomes unstable. So the simplest Pawlowski and Philander scheme uses zero order. It uses zero equations, so you don't have to solve any equations. It basically, the viscosity and the diffusivities are parameterized in those two equations. So they are only a function of a Richardson number. And V max and V mean and K kappa mean are the minimum and maximum mixing coefficients you specify. So next up, in terms of sophistication, is a 2.5 equation closure models, such as Miller-Yamada scheme. It basically assumes that the turbulence mixing is related to the growth and dissipation of TKE, turbulence kinetic energy, and volume Orbikov mixing length L. So the TKEK and the mixing length L are governed by the second moment turbulence theory. So they look pretty much like a conventional transport equation with source terms here. And epsilon here is the dissipation rate, which is related to a TKE and L. M square is a shear frequency, N square is a buoyancy frequency. And in this scheme, you also have this unique thing of wall proximity function psi, which is a function of a distance from the wall. The two walls being the surface and bottom. Okay, that's this dB and ds is about. And then after TKE and mixing lengths are found, the viscosity and diffusivities are determined by this, TKE and L, as well as stability function, SM and SH. Okay, stability function, in turn, a function of essentially the GH. GH is nothing but, if you look carefully, that's nothing but the Richardson number. Okay, And also typically we apply, for Miller-Yamada, we apply this so-called Gauss-Green clipping, basically by limiting the value of this Richardson number. Okay. So this is a recognition that the scheme is not stable enough for outside this range of Richardson number. Okay, so you have two differential equations for TKE and L. So you need vertical boundary conditions. So the vertical boundary condition for the TKE is relatively straightforward. It's related to the frictional velocity or the Reynolds stress there. Okay, B1 is constant. And for the mixing length, we assume that it approaches the distance from the wall with a scaling factor. Kappa 0 is the von Karman constant, which is approximately equal to 0.4. Okay, so here is one of the problems in the turbulence closure theory. Okay, so because in a typical numerical method, we assume that the mixing length is on the surface and on the bottom approaches to the distance from the wall, right? But the L can be arbitrarily small, so L can be very close to 0, and this introduce some kind of singularities. I think most numerical model just gloss it over by applying the surface layer or half a surface layer, these kind of things. I haven't found a satisfactory explanation of how this theory works in a numerical model, really. And the initial condition is also important for this turbulence closure equations. And this is what I got from biradial Lambro papers. Okay, this is actually from Yumnov and Burchard papers. This is the initial values they used for Miller-Yamada. And psi, the variable psi will be explained in next slide. Slide 21. Okay, Yumnov and Burchard basically is a more generalized scheme, 2.5 equation schemes. So Miller-Yamada is a special case of this Yumnov and Burchard scheme, and so is K epsilon or K omega or even KPP. So the major difference between the Yumnov and Burchard closure and Miller-Yamada is that in Yumnov and Burchard scheme, second equation is not for the mixing length, but for so-called generic length scale psi, which is function of TKE and L here. And P, N, and M are constants. Okay, so different scheme will use different P, M, and N. So for certain choice of N, this exponent N, you need this wall proximity functions as in Miller-Yamada. This looks very much similar to Miller-Yamada scheme. And after the K and psi are solved, the mixing length L can be solved. Then the mixing coefficients, the viscosity diffusivities, are again related to the stability functions, C mu and C mu prime. And there are different choices of stability functions. Basically, stability functions are derived by assuming that there's a steady state for the two differential equations. But you can make different assumptions that lead to different schemes. So for example, what I showed you here is from the Kazai-Claisen scheme, the stability function. Okay, so pretty much similar to Gauss-Prince, but it smooths Gauss-Prince stability functions and approaches its maximum value, the maximum Richardson number. Okay, so this table, the two tables actually show you the choice of the parameters P, M, and N. Okay, for different closure schemes, and also it shows you the what the generic length scale parameter psi is within each scheme. So for the K omega scheme, it's the dissipation omega. Okay, that's a psi, and it's not dissipation; it's the time scale of dissipation. And KL is the Miller-Yamada. If psi equals KL, that's why KKL is basically Miller-Yamada. But in the framework of Yumnov and Burchard, if you choose psi to be epsilon, that's the dissipation rate, then it becomes the K epsilon closure of Roddy. Okay, and the K tau, if psi equals K tau, then it's K tau. Okay, so the major thing you want to notice there is that the parameter, the sign of the constant n is important. So if n is positive, then you need to use a wall proximity function. Whereas if it's negative, you don't need to use wall proximity functions. And the next table shows the various parameters. Various, this is bad. It shows the constants used in each scheme. Okay, so I apologize. This slide looks a bit funky, but say the important parameter is C psi 3 minus C psi 3. Okay, and this parameter here. Okay. The choice of this parameter is a bit complicated. Okay, depends on whether or not the fluid is stable. Okay, if it's unstable, then it takes a value of 1. So if it's stable, then takes a value that depends on the schemes. Okay, then the last part of the lecture, I don't know how much you know about GFD, but I like to briefly review some important features of GFD. Okay, and as I said, Coriolis plays an important role in GFD. So one way to derive those dimensionless parameters is to use the Coriolis, the factor f. Okay, so this is one way of. There are many ways, other ways of deriving the dimensionless parameters. This is just one way, and used in GFD. Okay, so the capital U here is the velocity scale, and capital T here is the time scale, and L is the horizontal scale, and capital H is the water depth and the vertical depth scale, the vertical length scale, and capital W is of course the vertical velocity scale, and omega here, capital big omega here is the Earth's rotation rate. Okay, and mu here is the viscosity. So if you use these scale numbers, then you can get those dimensionless parameters. Those first two are the Rossby numbers, and the last one mu over omega h square. That's called Ekman number because it's only important in the two boundary layers. Okay, where the viscosity becomes important. Interior of the flow is essentially inviscid. But inside the bottom boundary layer and the surface boundary layer, the viscosity becomes really important. And like I said, this is not the only way to derive dimensionless numbers. Another way, if you use length scale and the velocity scale and the viscosity, combine them, you can get the all-important Reynolds number. Okay, Reynolds number, if it's very close to, if it's small, then that means the viscosity is very important, right? Small Reynolds number means the viscosity is important, whereas a large Reynolds number, that means the viscosity is not important as compared to the inertia. UL is basically inertia. Okay. And for large Reynolds number, the turbulence becomes really important. And if the turbulence is important, then AD viscosity typically dominates the molecular viscosity term. Okay. And then if you read the literature of GFD, one of the important terms you like to use is geostrophy. Geo basically means Earth. Strophy means rotation. So basically geostrophy means Earth rotation. Geostrophy is basically assumes that the flow is rapidly rotating, so Coriolis is dominant. Then you neglect the viscosity term, and neglect the. If you further assume that the fluid is stable, a steady state, okay, there's no temporal derivative term, then you can get this set of equations. Okay, and then you can derive this Taylor-Proudman theories. Basically, says the fluid is vertically rigid, because there's no vertical variation of velocity. And in this case, if the flow is rapidly rotating, then flow is along the isobars. Okay, the isobars should be isobars. Yeah, along the bathymetry. So streamline is basically same as isobars. And there's no work done by the pressure and no energy required, so it's inertia. Okay. Once it's generated, it can last forever. Of course, in real world, you have a viscosity that that takes some energy out. And if you look into detail, you can even predict the rotation around the flow direction along the isobars. Okay, so if you have high pressure in the middle, then the flow must be, in the northern hemisphere must be clockwise, etc. Okay, the Ekman dynamics are important in a viscous layer. That's the bottom boundary layer and the surface boundary layer. So you have a surface Ekman layer and a bottom Ekman layer. And then if you assume that the flow is steady and homogeneous and a uniform interior, then you can simplify the momentum equation to be this form. Okay, and those are the two vertical boundary conditions. And you solve it, you get this Ekman solutions. Okay, so if you look at the solution, we are now on slide number 26. If you look at the solution, the velocity actually dependent upon the viscosity. If the viscosity is very small, that means the flow is almost inviscid. The surface velocity can be very large. And also the surface velocity makes a 45-degree angle to the wind direction. And if you look from the top, then you can see spiral structure of the velocity, and you go down water column. Okay, and rotation is to the right in the northern hemisphere. So as you can imagine, for the bottom Ekman layer, the rotation will be done on the opposite direction, right? And if you integrate across the Ekman layer, you can get a lead transport. And the interesting thing about the Ekman transport is that it's perpendicular to the wind direction. Okay, so don't know how much you know about the waves, but here are some fundamental about the wave mechanics. We are now on page 20, slide 27. So if you take this simplest case of 1D wave, okay, the plane wave, eta is a function of cosine. It's a cosine wave here. The simplest case. A is called amplitude, and kappa is called the wave number vector. So it has two components in a 2D plane, L and M. Okay, and omega is angular frequency related to the period of the wave, and phi is the reference phase. So the whole thing is called a phase, Lx plus My minus omega t plus phi. So the phase line is determined by this phase equals a constant. So it's a family of straight lines in 2D plane. Okay, and I show here. So the distance between the two wave crests of adjacent wave crests, or for that matter, any lines that corresponding to the same phase, is called the wavelength. The wavelength is related to the wave number. Okay, 2 pi over the kappa, the wave number. So next slide, 28. So the speed, the phase line, a particular phase line propagates, is called phase speed. So from the equation for the phase 9, you can easily calculate the phase speed is a function of angular frequency and wave number. So it's omega over kappa. And it's in the direction of the wave number vector. And in many GFD systems, you have this so-called dispersion relationship. So the angular frequency is a function of the wave number. Okay, so that's called a dispersion relationship. For example, for the surface long gravity wave, I mean, for the surface wave, you can get omega squared equals kappa g kappa tan hyperbolic tan kappa h. Okay, so as you can see, if omega is a linear function of kappa, then the phase speed will be constant, right? Will be constant. If it's a linear function of kappa, then phase speed c will be constant, regardless of the value of omega kappa. So waves of a different period will travel at the same speed, phase speed. Okay, that's called long dispersive wave. Otherwise, it's called a dispersive wave. Okay, because the wave of different period will travel at different speed. They will disperse over time. So one example of a non-dispersive wave is the tides. It's an ocean wave. Okay, the concept of a group velocity is pretty important in wave mechanics. We're now on slide 29. So first of all, the wave energy is proportional to the amplitude squared. Okay. So if you take two one-dimensional waves, equal amplitude but very close wave numbers, okay, or wavelengths, wavelengths very close to each other, you sum them up and you use trigonometric properties, you get this. So the last term is the same as it's basically cosine wave term. Okay, nothing special. The wave wave number is kappa and omega is the angular frequency. Whereas this part 2a times cosine, this thing can be considered as an amplitude. It's a slowly varying term. Okay, because delta kappa and delta omega are very small. So it's a slowly varying term. So that means the amplitude of the envelope, this envelope varies very slowly. So that leads to the beating. So the delta omega is called the beating frequency. So that's the origin of a spring leap cycle. Okay, because you have waves of very close periods. And the speed, the envelope or the wave energy travels is called group velocity. So group velocity is delta omega over delta kappa, right? This is the speed of the envelope. This is the envelope speed. So if you think delta kappa and delta omega are very small, then this is you get this formula. So the group velocity is actually the derivative of the angular frequency. Okay, the phase speed is simply omega over k, whereas the group speed is d omega dk. Okay. And phase speed determines a particular phase, how fast the particular phase travels, whereas group velocity determines how far the energy travels, radiates from the source. Okay, so those are different concepts. Okay, next slide, slide number 30. And I'd like to show you some linear wave series and simplest theory you can find. So you linearize by assuming that the amplitude is small and the motion is homogeneous, and then you can, is harmonic, and then you can get this linearized shallow water wave equation. And you can simplify it by assuming that the water depth is constant in the simplest case. Okay, that's the barotropic wave on a flat bottom. And if you further neglect the Coriolis, you get the classical wave equation, and the wave speed is square root of gh. So it's a non-dispersive wave because the phase speed is not a function of wave frequency, right? So it's a non-dispersive wave. So in the coastal ocean, next slide, 31. In the coastal ocean, Kelvin wave is also important. Kelvin wave occurs typically in a semi-implicit. So you have an ocean bounded by a coastline. So Kelvin wave can travel either direction. Okay. So if you make some assumption that the bottom is flat and the coastline is free slip, and you can simplify the momentum equations to be this form, okay? And then this form, you can solve it. You get this u and the v and eta is a function. It has an arbitrary function in the f. Okay, f is an arbitrary function. Okay. What it says is that the shape of a Kelvin wave can be arbitrary, but the propagation speed is constant. Okay, propagation speed is square root of gh, it's the same as a gravity wave. And the scale of the Kelvin wave is determined by this capital R, which is called the Rossby radius of deformation. It's nothing but the ratio between the wave speed and the Coriolis factor. So, and I said that the Kelvin wave can travel either up or down the coast in two directions. And usually, typically it's generated by the ocean tides and by the wind. Okay. Any questions so far? I want to make sure you guys have time to ask questions. Okay, so next we go to the stratified system. Okay. In a stratified system, one of the most important concepts is the buoyancy frequency. Okay. So you suppose the density is a function of z, right? And it's neutrally stable. That means there's no initial motion. And then you displace a fluid parcel from its original location up, because the density, when you go up, the density will become lighter, and you have restoration force, which is a balance between buoyancy and the gravity, right? The restoration force will pull the parcel back towards its original position. But when it reaches original position, because of the inertia, you overshoot and come back. So the wave motion will be resulted. And if you write a simple equation from the Newton's second law, it's basically F equals ma. You can get this, and you simplify it. This is nothing but the classical wave equation. And the frequency of oscillation is called buoyancy frequency. It's like this, minus g over rho 0 and d rho dz. Also called Brown-Weissala frequency. Okay. So this, in turbulence closure especially, you see lots of this kind of n square, that's buoyancy frequency, even in the definition of Richardson number, right? On top you have this buoyancy frequency. So if buoyancy frequency here, n square is greater than 0, then it's stable stratification. Whereas if it's negative, then the stratification becomes very unstable. That means a little bit disturbance will permanently change the initial state. Okay, and lastly, about the internal waves, slide 33. Okay. So for internal waves, you need to you cannot neglect the vertical acceleration anymore, as you did in the hydrostatic assumption. Okay, so you need to keep because vertical acceleration is a major driving force in the internal wave. So what you do is you take the density rho and hydrodynamic pressure and do perturbation around its mean state. It's rho prime and p prime are the perturbation. Okay, assume that perturbation part is much smaller than the mean state. That's typical perturbation approximation, and then you plug back into the momentum equation and the continuity equation, you get this static equation, and then you assume that everything is linear. The amplitude must be small, and you try to find this kind of harmonic solutions. Okay, so L, M, and Z, L, M, and N are the wave numbers in X, Y, Z direction, and omega is the angular frequency. You solve this, you plug it back, and you solve it, you get this dispersion relation for internal waves. And one interesting thing about this is that this, if you look at this is nothing but the angle made by the wave number vector to the horizontal plane. Okay, and also the maximum angular frequency is this n squared, because this one is always less than 1, right? So maximum is bounded by the buoyancy frequency. And in terms of dispersion relationship, I just explained the omega is actually only determined by the angle made by the wave number and the horizontal plane. And if omega approaches 0, that means the theta, the angle goes to 90 degrees, so the motion is purely vertical. You can internal wave propagating along the vertical direction. Okay. And so here are the full solutions from the perturbation expansion. And if you look in detail, you can see that the internal wave is always transversive, and group velocity is always inside the phase plane. That's one property. And in a special case of n equals 0, that means the vertical wave number goes to 0. Let's say the group velocity becomes 0. That means there's no energy radiation. And one thing I like to point out is that for continuously stratified flow, which is different from the two-layer flow, you can have infinitely many modes of internal waves. Okay. So you can have many waves of many frequencies. Of course, those frequencies must be bound by the buoyancy frequency. But other than that, you can have different frequencies, infinitely many frequencies. That's about it. Are there audience in remote site? I think they all lost connection. Yeah. Well, too bad. So next, to give you some preview, next lesson we will talk about the numerics. Okay, that's the meat of the presentation, the course. I'll put the slides online, okay, as soon as possible, so you guys can have a time to review it. So you can ask pertinent questions, because I think the course is the most effective if you guys can ask questions. Otherwise, you can just sit at home and listen to the audio of this talk. Yeah. Yeah.
Time to look at
Yeah.
video beforehand, prepare to get some questions for you.
Yeah. Yeah, I'll try to put all the rest slides for the rest of the lessons online. Okay, next 2 lessons at least.
Now, a lot of this stuff in the physical formulation are going to come up again.
I'll try to review in the context of numerics. Yeah, but the reason I really want you to understand the physical formulations, and I truly believe that physics and numerics are interconnected. Really, if you don't understand physics well, no matter how you tune the numerics, you won't get it right. If you yeah, so it's important to actually have some level understanding for the physics, especially turbulence. Also applies to wave mechanics. It's pretty important.
Should we go back to turbulence?
Sure. This one.
So, 3 KKL, K epsilon, and K omega
Mm-hmm.
basically distinguished by how the
Yep. How you define the scale variable psi, and how you choose some constants, like say mu 0 and sigma, or those constants here.
and you were just, so K omega is the time scale of dissipation, is that?
Omega is the time scale for the dissipation. Yeah. Yeah.
And so the cases where the length scale is where you're using the inverse of the length scale, it doesn't have a singularity because as you get close to a boundary, the length scale gets smaller and smaller, so the variable that you're actually tracking gets larger and larger rather than...
But the origin...
That's why the negative sign doesn't cause...
No,
negative
negative sign because you see this is a negative sign here. You see that L is mostly on the denominator, like K psi. Yeah, L is mostly on the denominator here, epsilon. Yeah. So if L is if the psi is negative, then you can multiply through by L. You know, if you do some manipulation, actually they cancel out. You know. So, yeah.
But, and that's based, I mean, the... Right.
Yeah.
And so what is... Epsilon is the dissipation rate?
Dissipation rate, yep.
Okay.
How it determines how fast the turbulence energy, the turbulent kinetic energy dissipates. Yeah.
And that also gets larger as you get closer to the wall. Okay, that makes sense.
Yeah. Yeah. Yeah, if you have friction, yeah, you dissipate much faster. Yeah. Whereas if it's inviscid, it can propagate forever. Right.
And what is KPP?
KPP is a new scheme for the. It's basic. I think Scott, if he's here, he can explain. He's the author of the KPP. It's basically, my understanding is that it's the only non-local, because everything here is, you see, these variables are evaluated at local position, right? So the TKE and L are mostly affected by the local variables. KPP is the only one that's non-local. So it's basically recognize that what happens in this point in space may be related to somewhere else, you know, not very close. You know. There are definitely other differences in how the KPP is derived, but I think that's a major difference. We have time for some questions.
What are the, I'm trying to figure out all the variables. What are the capital E in slide 19?
Oh, those are constants. E1, E2, E3. Those are constants.
And where do they come from?
It's calibrated. You calibrate it through experiment or through theoretical work. So are the those constant G2, G3, G4, G5, G6. You know, those are all constant.
And is this wall proximity function, whatever you call that, what do you call it? It's, what's that letter?
Psi, psi,
Psi?
psi. Yeah.
Psi?
Yeah.
Psi. So is that the same as we see in...
No, no, that's different. This is capital psi. Yes, another one is you see, it's a small psi. It's different. Here I even use a different walk point. Yeah, so I use the F wall. Yeah.
It does look different.
Yeah. Yeah. Yeah, F wall probably is more clear.
And when we're looking at the viscosity term, the dk over the total derivative of k over 2, and then there's the equals, what is that viscosity?
This one?
Yeah.
Yeah, that's the diffusivity, one of the diffusivity.
The power of psi.
This is not power per se. It's just the whole thing is a symbol. Yeah. Yeah.
Oh, okay, you said it's not a power, it's just a subscript.
Superscript. Yeah. Here, m squared, n squared, those are powers.
Yeah. Oh, okay, I was just comparing it to the viscosity term right below. The V right below, where you have it as a subscript. That's what I was
Right, right. Yeah, there are lots of details in how you implement those turbulence closures, and they all matter. I know that firsthand, because when I implement the Umlauf and Burchard closure itself and compare with Umlauf and Burchard's results, they are different.
So how does I'm trying to see where the psi variable connects back into diffusivity in general.
Side variable.
The one on the
Oh.
top, the one with the red box around it.
Yeah, yeah.
How does that connect back into mixing?
Those terms? You mean those terms?
Okay.
Nu, kappa, and this one, is it? Diffusivity terms? Those terms, you mean? Is that right? Psi is a function of L. Once K is solved, then psi is solved, then you can find L, and you plug in. Yeah. Yeah.
C naught is the first term is a constant.
C mu 0, you mean? Yeah, it's a constant, scaling constant. Yep. Yep.
K is something you calculate.
Mm-hmm. Yep.
Something you find when you get K, P, M, N are all constants.
Right.
K is something you calculate how?
From the transport equation.
That
Yeah.
comes out of the transport equation. For,
Yeah.
Wait, can you solve for L is
That was what you're looking to solve, right? That was
Yeah.
that was the goal.
Oh, L is go, yeah.
K comes
Right.
out of the transport equation.
Yeah.
It's just the velocity, the kinetic energy function. of
TKE.
velocity.
It's not velocity, it's turbulence velocity. You know, it's a u prime square plus v prime square plus w prime. So turbulence fluctuation component of the velocity. It's not mean velocity. Yeah, so that's why it's called TKE. It's not KE, it's TKE.
How do you get turbulent kinetic energy out of the momentum equation?
It's not from momentum, it's from this transport equation.
The transport equation.
Yeah, you just solve it. Yeah. Yeah. I'm going to ask it to stop the recording. Jeff, it's done. Oh, actually I pressed. Oh, shoot. All right, we should get started. I don't know, for the remote side, I don't know how many of you can hear me, but I just sent an email to all attendees. You know, they